Hello everyone, my name is Amir Doriani. I'm a PhD student at University of Florida. Today, I represent CaMuViD, a calibration-free multi-view detection framework. This work addresses one of the biggest bottlenecks in multi-view perception, which is dependency on accurate camera calibration. Before going deep to our method, I need to have a good introduction to our research area. In our research area, occlusion is a major problem in pedestrian detection, especially in crowded scenes. Traditional methods often rely on single camera and miss individuals which are obscured from views. So in this way, multi-view detection methods improve robustness, but it depends heavily on synchronized and calibrated camera setups, which are hard to maintain in real-world scenarios and environments. Let's look at the limitations of the current methods. First of all, they need prices camera parameters, and errors in calibration cause projection distortions in birds of view space. Also, they are not flexible for changing environments or mobile cameras, and if you do this, it costs you lots of computations. Also, birds of view based models miss view specific features. Because of this, our goal is to address all of these problems without using camera parameters at all. In overview of our method, I need to tell you that our method needs n views, n camera views, and we will feed these end view images to backbone for feature extractions, and after that we will apply projection estimated matrices to each extracted features to change a space. This projection estimation is calibration free. They just rely on extracted features. After that, we will have feature fusion because we want to aggregate all of the informations from all of the views to one space and use these aggregated features for to have a better detection method, detection performance for each views. But we are in a shared space. We cannot have a detection for each view because we have information for all of the views. What we should do? We should go back to each specific camera view perception. Because of this, we have a back projection estimation, and we can back projected features for each view, and then have a detection very easily. But we have another problem. We have extra information from other views that may cause some low activations in feature map. Because of this, we have refinement network to refine the features map for each view, and then after that we will have detection head for the prediction of the bounding boxes. In this slide, you can see more details about our architecture of our method. So, as I told before, we have a backbone for feature extraction, and after that, we have a projection matrix for each feature map, and we projected these feature map to share a space, and we will have concatenation as a fusion method. But after concatenation, we have huge size of the channel size. that is which is not suitable for us, because all of the detection head except 256 channel size, and we will need to reduce the channel size, this concatenated feature map channel size to 256. So we applied simple convolution for the kernel size of the 1 by 1 to reduce channel size. And then we will apply back projection matrices for this feature map to go back to each camera perceptions. And after that, we will have refinement network and detection head. As you can see, we have n different refinement network and n different detection head for each camera's perceptions. Because of this, we have a specific camera perception, bounding box projection, and they are independent from each other. For purpose of projection and back projection, we should ensure that back projection matrices are inverse of projection matrices. So we use these inversion loss functions alongside other loss functions of the traditional detection methods, such as bounding box and classification loss function. This loss function ensures that the multiplication of the back projection and projection network is identity matrix. Also, we have the same network for projection and back projection. The figure A shows this network. This is simple, fully connected network with ReLU activation functions, and also the projection and back projection matrix multiplying is channel-wise. So the output of this network is 256 by 256. And for refinement networks is a simple convolution network with 2 layers of the convolution and 2 ReLU activation. The most important part is that the first convolution layer is 7 by 7 for kernel size, and it indicates that we want to see large size of the features map to reduce and remove low activations features and have a better and smooth activation maps. For experience, we use 2 different datasets. The first one is Wildtrack, which is a real-world dataset with 7 camera setups, and the second one is MultiviewX. MultiviewX is a synthetic dataset with 6 camera setups. The goal of the MultiviewX is that we won't need any more real-world multi-view camera setup, because it's so hard to collect this kind of data. It has some privacy problems and something like this. And if you have a good performance in MultiviewX, you have a good performance either on the real world. We can see it in the future. So for training and test configuration, we have 90% of the first frames for training and the last 10% for the test. And for evaluation, we have MODA metric, MODP, F1 score, precision, and recall. As you can see, we got the state-of-art result on MODA in recall and F1 score for both of the data sets. The reason that we don't have state-of-art MODP is that we are evaluating our method on the image space in the bounding box level, which is IOU. It is harder to align bounding box for IOU. But all other methods, they are working in birds of view space, which is just simple point, and getting closer to the point is easier than getting closer to bounding box. The reason that we want and we cannot evaluate in bird's eye view, you can say that we need just simply project our bounding boxes to real world and compare in real world. No, it's not that much, because we have calibration errors and also we train on the ground truth bounding box, which ground truth bounding box has a error with real world point, and all of these error will go add to each other and increase our errors in overall, and we cannot show that our real performance, because our method trained on the bounding box, ground truth bounding box, not the real bird's eye view point. And all of these we know we cannot add all of these errors to our performance. This is a qualitative results. You can see that we are detecting very good bounding boxes for most of the cases. We have another good experiments that show that the first row showed the projection and back projection fusion for camera calibration parameters, and for our method we just replace camera calibration parameters with for projection and back projection purpose for our diagram. And we can, and also for the second row is our method. You can see that our method doesn't estimate camera parameters. There are two different things. We are working in two different space. So we are working in the feature space, and we are not claiming that our method is estimating camera parameters. And you can see that if you use projection matrices, camera parameters for our method, you cannot have bounding box information for back projected featured map for each view. Also, we have done some more experiments, which one of them is that shows in table 2, number 2. We train our method on MultiviewX and we test it on Wildtrack. This is so interesting. We can train our method on statistic data and test it on real world scenario. This is perfect. And you can see that our method got a better performance according to in comparison to other methods. Also, we had some more experiments for camera illumination. It shows that we don't need always all of the camera views. Sometimes 6 camera views is better than 7 camera views in terms of performance. Thank you for your listening and consideration. You can scan this barcode for more details and code. Have a good day.